Hello, dear IEEE Comstock Distinguished Lecture Program Chair. My name is Guang Gui. I come from Nanjing University and of Post and Telecommunications. I'm the IEEE Fellow, IET Fellow, and Professor at the university. My research topic is focused on ubiquitous sensing and intelligent identification techniques for 60-watt communications towards lower source radio frequency machine learning system. This briefly introduce my laboratory and me. Uh, I have been involved in many international conference as being the track chair, vice chair, and the executive chair for a lot of conference, and also I work for some international journals and the editorship. This is briefly introduce my research background, framework, and key technologies and future work. As you know, electromagnetic spectrum is the foundation of what telecommunications technologies and is crucial for broadcasting, mobile communications, satellite navigation, medical imaging, and many other modern technologies. So traditional expert systems that rely on specialized knowledge to formulate rules are difficult to adapt to complex systems. Therefore, it becomes crucial to explore deep learning based on spectral big data. In August 2017, the US DARPA set up the radio frequency machine learning system we call the IFMS. The goal of IFMS is to develop a foundation for a platform data-driven machine learning to the radio frequency spectral domain, including radar, signal intelligence, electromagnetic wave, and communications. So several US electromagnetic spectrum spatial intelligence labs have focused on radio frequency machine learning system in recent years and have made some very important contributions in this topic. However, we face several challenges for studying radio frequency machine learning system. The first one is data requirements. So AI models require massive amount of the high quality data. In July 2023, the number of the large data centers worldwide has approached 900. The amount of training data required for OpenAI's GPT has increased from 5 gigabit to 14.5 TB. And the second one is computational power. AI models are computational complexity and require high computational power from the 2012 to 2020. OpenAI's computing power is increased by 300,000 times over 8 years. And also in March 2023, the computing power for training the large March model GPT-4 reached to 12 big size flops per second. So the third one is storage requirements. This is no grace in storage performance compared to GPT. Computation power has resulted in storage access speed become a bottleneck for AI performance. So it is better it is required to develop a lower source radio frequency machine learning system. So in below 4 aspects. The first one is machine learning means signal processing, and the second one is machine learning should meet lower source scenarios like tiny machine learning. And the third one is signal processing means lower source scenarios using suboptimal algorithm with lower complexity. And the last one is machine learning and signal processing should match lower resource scenarios. Does it really work in practical applications? So in this case, we considering the framework of the lower source radio frequency machine learning system from the different aspects like application layers, architecture layers, model layers, data layer, and physical layers. So the below this slide introduces some of the key technology of lower source lower resource radio frequency machine learning system. The first one is computing for computing and storage limitations. We reduce the model size and the computational complexity by pruning, efficient convolution, knowledge distillation, and so on. The second one is for data and level limitations. We improve performance by develop semi-supervised learning, imbalanced class learning, few-shot learning, self-supervised learning, and data augmentation, and so on. So in this case, we developed a lightweight model design method. So we call the ultra-light convolution neural network for automatic homogeneous classification based on efficient evolution, channel shuffling, attention mechanism are used to compensate for the performance loss of the compact recognition model. So our proposed method can achieve the almost same performance as the state-of-art method, but the parameters and the other parameters almost decrease by an order of magnitude. And the second one, we proposed a joint optimization method for lightweight signal recognition model based on proximal gradient and knowledge distillation. The proposed method can remove redundant neurons, compress model size, and maintain advanced performance. So in here, we propose a new architecture search-based lightweight automatic modulation recognition method. So this method can automatically search for the optimal neural network based on single samples. The proposed method can achieve the highest recognition accuracy while can use lower parameters and flops. So here we propose a new method. So we call this method is GPU-free broad learning. So we can use network characteristics of single layer forward propagation in widened learning. So we propose the method nonlinear enhancement node and signal feature nodes can has been introduced significantly improve accuracy of broad learning system for specific image identification and while reducing the parameter and complexity of the signal recognition model. So the fifth method is our proposal. We use a hybrid data augmentation. So in detail, the proposed method is linear transformation and interpolate blending to expand the training samples can improve the performance and beam selection in wireless communications. So this one, in this slide, we proposed a semi-supervised recognition model based on metric advanced training. So for solve the problem is the label is missing and label is affected by other the noise. So we introduce side labels into metric learning and automatically recognize objective function by metric learning and virtual advanced learning to extract discriminative and generalized semantic features of radio signals. So here is another one. We propose another advanced semi-supervised learning based on the dual consistent recognition. This most of the details are a little bit similar to the last one, but here we considering the consistency between the semantic feature distribution of labeled samples and that of side labeled samples. And this one, we proposed a few-shot learning signal recognition model based on metric ensemble learning. We use a dual semantic similarity consistent mechanism based on triple loss function and center loss function to enhance inter-class variability and intra-class consistent of signal samples in the symmetrical feature space. Here we first use proposed few-shot learning signal based on the self-supervised learning and the advisor argumentation to improve the generalization of capability of self-supervised learning and the recognition accuracy in few-shot scenarios. And here we also proposed another few-shot signal recognition method based on a symmetric mask autoencoder method. We utilize a large number of unlabeled symbols in the source domain for self-supervised pre-training and then fine-tuning with a few short emitter samples in the target domain, significantly improve the accuracy of electromagnetic signal recognition and few short conditions. So for each work, we will focus on multi-model sensing. So the advantage of the multi-model sensing lies in the comprehensive utilization of different sense models, improve the robust and accuracy. By integrating and analyzing multiple sensing results, more comprehensive and reliable information can be obtained to support spectral measurement and wireless communication system optimization. The second one is how to use joint data-driven and physical constraint models. So one of foundational data-driven models, constraints and limitations are applied to spectral perception based on the physical laws of electromagnetic wave propagation and spectral utilization. So another one is how emerge novel source-aware architectures, such as use the GPU, the GPU free or CPU, and also like brain-inspired networks, theoretical networks, and quantum networks to reduce the computational power. So this end of the my presentation to briefly introduce my research topic. So thank you very much for your attention. This end of my presentation. Thank you very much.